Handouts for you this week, so you'll be making your own notes as we go through. Yeah, you got to concentrate, but these board notes will be put up post session as soon as I get the time to do so. All right. So, AC circuit analysis. We're going to be popping back to go over some of the ground we covered in the electrical half of science 2 years ago, not last year, the year before. Okay, so perhaps building on that a little bit. So we're going to be looking at complex number arithmetic this week. Okay. Joy of joys. So we'll go through each of the basic components that you might have in an AC circuit. So if we had an AC circuit with just a resistor R, okay, we need to start considering now whether we're talking about maximum value currents voltages and whether we're talking about a current at an instant in time. If we're talking about a current at an instant in time, we have to use lowercase I, or a voltage at an instant in time, lowercase v, to represent those values. Okay, so we have a current flowing in that circuit, and if we drew a phasor sine wave, if we plot the sine wave of the voltage and the current over time, green sine wave is V, little v, blue sine wave on the same axis as little I. Okay, they are in phase with each other. So they both peak, the current and the voltage peak and cross the x-axis in the same place at the same time. So they're in phase. And we can draw a phasor diagram such that the current I, represented on the horizontal axis, and that should be capital I because we're talking about the length of that line is the peak of that waveform. Okay, the peak value, so this current at this height here, and the voltage waveform like so, in phase. So they're represented at 0 degrees on the circle, because that's 0 degrees when we go horizontal left to right. Okay. What we need to make note of is, in AC circuits, we change from resistance R in ohms to impedance Z, also measured in ohms, for the overall opposition to current flow. Yeah, so that's what resistance is in a DC circuit. It's the opposition to current flow, the restriction to current flow. In an AC circuit, we'd refer to that as impedance to be technically correct. Okay? We can then have what we call an impedance diagram. For pure resistance that has the resistance R at the 0 degrees portion of the phasor. Yep. This can be represented by represented in two ways as R angle R ohms angle 0 degrees or 0 radians, or R plus 0J ohms. This being polar form and this being rectangular form. Okay, so just to summarize for clarity, if we have an AC circuit with just resistance, we end up with a voltage and a current waveform that are in phase with each other, i.e. they cross the x-axis at exactly the same time and in the same direction. The phasor diagram has both the voltage and the current phases left to right on the phasor diagram, or at 0 degrees. In AC circuits we change from using the term resistance in ohms to using impedance Z in ohms for the overall opposition, but that Z can be made up of some resistance and one or other of, or both, of capacitive and inductive reactance that we're coming on to soon. Okay, all those quantities measured in ohms, but are all slightly different in some way. The impedance diagram for a pure resistance circuit is a single phasor left to right at 0 degrees, and we can represent that mathematically by the resistance value, its units at a particular angle, polar form, or its resistance, i.e. this, you'd say this is the horizontal component as another way. And that being the vertical component. I.e. these rectangular is how far is it that direction, yeah, and how far is it in the J direction, horizontal, vertical. We can go negative horizontal and we can go negative J in that direction too. Okay, so it's two different ways of representing those complex numbers. All reasonably happy with that so far. It should jog some memories about stuff from engineering science, hopefully. Moving on. If we had a circuit that only had inductance and an AC sine wave applied, so that is inductance L, okay, and applied AC voltage. If we do the same thing and put that on a sine wave diagram, if we have, I need to mark 90, 180, 270 and 360 degrees to help me draw my waveforms. The voltage in the same place as it was before. Okay, our current would be 90 degrees out of phase, and it actually lags behind the voltage by 90 degrees. Don't get confused by the fact that the blue one appears to be ahead. Remember, that direction is later in time. So the blue waveform crosses the x-axis after the green one. The current is lagging the voltage. Okay? We have a phasor diagram where we can choose whether we put voltage or current as what's termed the reference phasor. We could decide we want to make the current start at 0 degrees and then have the voltage leading it. It doesn't make any difference which way, but for the benefit of this, we're going to keep the voltage on the horizontal axis and show that the current I is 90 degrees out of phase with the voltage. Current lags V by 90 degrees. The impedance phasor will show where our reference 0 degrees is, okay, but we've got up here ZL, that's equal to XL, the inductive reactance, which is equal to 2 pi FL, where F is the frequency in hertz and L is the inductance in henries. Yep. We maintain the fact that an inductor has an angle associated with it of 90 degrees. Positive. Okay? I'm going to summarise that a little bit clearer here. ZL equals XL equals 2 pi FL. May also come across it as omega L. They're all measured in ohms. Impedance of inductor is equal to the inductive reactance F is the frequency in hertz omega in that bit is the angular frequency in radians per second. So omega, if you compare those two, omega must be equal to 2 pi f. And you've come across that before. Mathematically, we can represent ZL as being equal to XL ohms angle 90 degrees polar form, or ZL is equal to 0 plus XL J ohms. Rectangular. Okay, what you must bear in mind here is it's absolutely impossible to have a circuit with pure inductance, because an inductor is essentially a coil of wire like a motor or a transformer winding, and therefore that conductor has some resistance. It's not possible to have a purely inductive circuit, but theoretically if you could have one, you'd get exactly 90 degrees phase shift. Current would lag by 90 degrees. Can anyone remember the word we used in science to determine whether one was leading or lagging? Whether a circuit was going to be leading or lagging. We'll come back to that after we've covered the capacitive circuit. But there's a useful way to check whether your calculations are heading in the right direction. Okay, so we'll do that in a minute. Right, so moving on from, sorry, had you all got what you wanted from that page? Yeah, everybody happy? So moving on again, pure capacitance. If we have a circuit with capacitance C only, AC sine wave applied, current flowing, okay, we would end up with a sine wave graph, something like this. Voltage is the in-phase component. And the current I leads the voltage V by 90 degrees. Because this peak here is a whole 90 degrees before the voltage peaks. A phasor diagram where there's I, V reference phasor, 90 degrees between the two, and that shows that current leads by 90 degrees because our angles are positive going anti-clockwise around the circle. Yep. So current leads by 90 degrees. impedance phasor, (0° line for reference), ZL is equal to XC is equal to 1 over 2 pi FC ohms. So the impedance of the inductor is equal to the inductive reactance, which you can calculate from 1 over 2 pi FC, or indeed 1 over omega C. So to complete that like we did on the other page, ZC is equal to XC is equal to 1 over 2 pi FC is equal to 1 over omega C ohms. Impedance of the capacitor is equal to the capacitive reactance there's the frequency in hertz, and there is the angular frequency in radians per second, to make it complete and like we did on the other page. And we can write those things mathematically as ZC is equal to XC ohms angle minus 90 degrees, or minus radians as the case may be, or ZC is equal to 0 minus XCJ ohms. Rectangular polar forms. Okay, and again, it's not possible to have a purely capacitive circuit because we got the resistance of the wires, the plates that make up the capacitor, and so on to consider. Alright, so it's having pure inductance, capacitance is not something that we can actually have in any circuit. And in fact, absolute pure resistance is difficult to achieve. Sorry? Yeah, they are. Well spotted, Lewis. Polar. Rectangular. Alright, so okay with the three basic conditions that we can have and how they can be represented with phasor diagrams and in the two methods of complex arithmetic that you've come across before. Okay? Right. Let's have a look when we start to combine two things together. Series RL. If we've given the impedance of an inductor in ohms, our knowledge should tell us that's plus 90 degrees. Yep. 24 volts, angle 0. If you're not given an angle for one of the given quantities, your assumption should be that it's 0 degrees, usually the voltage applied. Okay? So, what we need to do is start to build a phasor diagram for this circuit situation. We've got, I'll keep to the colours we used before, V, a reference phasor. Yep. That's fixed. There's only one voltage in the circuit. Okay. So we've got volt drops, but there's only one applied voltage. And then we've got R. Ooh, hang on, Michael, take that away, take that away. IR, the current and the resistor, yep, in phase, remember, so in phase of the voltage, and we've got a current IL 90 degrees out of phase, lagging, minus 90 degrees. What we then do with those currents, complete the parallelogram there. And that is our IT that's flowing in that circuit. And that is the angle between that and the reference voltage phasor. The impedance diagram is that we've got R in ohms, horizontal, 0 degrees. We've got XL, 8 ohms, so R is 10 ohms. Again, we complete parallelogram, which in this case is a rectangle. We've got our ZT angle in there. Yep. That angle's negative and that angle's positive, but size-wise will be the same. Okay. So, how can we calculate the total impedance for this circuit? Two ways. What way would you go for? ZT. Find ZT. Pythagoras, yeah. So you could go ZT is equal to the square root of R squared plus XL squared. Yeah. Root of 10 squared plus 8 squared that's what I make it. Just check that, just in case I got it wrong. Summarise that for the recording. Calculate the total impedance using Pythagoras theorem. So this is that'll give us the length of the phasor. Square root of R squared plus XL squared comes out at 12.8 ohms. And then choosing the tangent ratio because they're given values. The 8 ohms of XL and the 10 ohms of resistance, rather than using cosine or sine, which would involve us using the calculated hypotenuse. So the tan of the angle is opposite over adjacent 8 over 10. So we do 10 to the minus 1 on that and we come up with 38.7 degrees. So how else could we do that? Same arithmetic. And one method might suit one question and a different method suits another question, depending on what's been asked for, or it might be a better preference for you. We also said ZT is equal to, or we can say the resistance is equal to that, and the upright is equal to XL. So we can go into rectangular notation with a J on the end there like that. So we can immediately say that that is R, 10 ohms, plus 8, the value of XL, that's a J, ohms like that in rectangular arithmetic. Alright, and then convert using your calculator. Remember how to do that? So, rectangular looks quicker in this case. Yep. Okay, now, how about calculating the current? What's the formula for current? Which form of arithmetic are you going to use here? Going to divide. Polar. Yeah. 24 angle 0 degrees divided by 12.8 angle 38.7 degrees. How do we do polar division? Yeah, you divide 24 by 12.8 and you do 0 minus 38.7. So it equals 24 over 12.8 amps angle 0 minus 38.7 degrees equals, what do you say that is, Lewis? 1.88 will do then, amps angle minus 38.7 degrees. Note from the positive impedance value, we end up with a negative current angle, so the current is lagging. We've got an inductive circuit, current lags. I believe we said that earlier, current lags in an inductive circuit. Anyone remembered yet what the word is that we use to check? Civil, yeah. In an inductive circuit, so we're looking over this right hand side here, voltage is ahead of the current in the word, voltage leads current. We could equally say current lags voltage. Put that on there. Or yep. And we've just done a calculation, and the final check on that is that an inductive circuit, because we've got no capacitance in this circuit, has given us a current with a negative angle, and therefore current is lagging the voltage, and so that's a little check that we've got our angles the right polarity. Yeah. Have to be a little bit careful with that when we've got both capacitors and inductors in the circuit, because that angle will be telling us whether the circuit as a whole is capacitive, i.e. there's more capacitive reactance in it than inductive, or vice versa. But when we've only got one type, that's a definitive check. Okay? So, are you all happy with that? Yep. So, RC circuit. $10 ohms, 6 ohms, angle minus 90. So now we're moving over to a circuit that's got resistance and capacitance in series. Phasor diagram. Voltage. Need to bring that down a bit. Reference phasor. IR. IC. Complete the parallelogram. for IT, the angle in there. This time we have a positive angle, so you end up with a leading situation. Current leads the voltage in capacitors. Impedance phasor has R, 10 ohms, it's the horizontal part, XC, 6 ohms, the vertical part, negative, by the way, for a capacitor, 90 degrees in there. The total impedance, ZT being there, and an angle in there. And again, if we wanted to find the current in this circuit, we'd probably go down the rectangular route. Now we've learned that that's the quickest way, wouldn't we? So we'd say ZT is equal to R minus XCJ ohms. That's 10 minus 6J ohms. Convert using the calculator. So that, after conversion to polar form, we got a total impedance of 11.7 ohms at angle minus 31 degrees. Negative angle seems to be right because we're talking about a capacitive circuit. Negative angle for the impedance. So then we can go IT, the V of a ZT. We'll go with the 24 volts we had before, specify it. Over 11.7, angle minus 31 degrees equals. So we can use that word civil as a check. In this particular question, we got a totally capacitive resistive circuit. We end up with 2.05 amps at angle plus 31. So we got a positive angle, we got the current leading the voltage, and it fits in with our check from the word civil. Yeah? Okay, everybody reasonably happy with that so far? Yep. So let's bring all our components together. 10 ohm resistor, 8 ohm inductor, minus 6 ohm capacitor, (24 volts, angle 0 degrees). Supply. Okay. Expression for ZT. Got a series circuit, so what do we do with all the impedances? Add them together. So we got ZR plus ZL plus ZC. If we want to write that in slightly different form, ZR is simply equal to R plus ZL is XL J ohms minus XC J ohms. And then for these two terms, J is common, so we can bring that outside some brackets. There's the formula for overall impedance in a series RLC circuit. Okay, and as you should be able to see from that if XL is bigger than XC, we'll have a circuit that's overall inductive, because this bit in total will be a positive number, and if XC is greater than XL, then we'll have a circuit that's overall capacitive in nature. Alright, so in the case of this circuit, impedance phasor. We've got R equal to 10 ohms. XL equal to 8 ohms. XC 6 ohms. Both of those at right angles. Yep. What we end up with is another quantity here. The overall reactance X is equal to XL minus XC, and in this case that's pointing upwards because 8 minus 6 is 2, so we end up with a positive value, so we end up with a positive overall reactance again, thus at right angles. So we combine our two reactances into an overall reactance, then we can complete to end up with ZT is equal to R plus X ohms. Yeah, and we got our angle in there again. And the sketching of a phasor diagram is always useful so you can actually quickly get whether your angle is positive or negative from sketching out the phasor diagram and know in which direction this overall reactance needs to be. You're likely, given a question along these lines in the exam, to be asked to sketch phasor and impedance diagrams and label them correctly. Yep, that's the sort of thing I'm expecting you to be able to do. You don't need to be a scale, you don't need to use a ruler, just need to make sure that you include all the necessary information. Okay, so once we apply that to the question, we end up with ZT is equal to R 10 plus 8 minus 6 J ohms. Okay, again, exam, don't drop the J off the end, don't forget to put it in there. Sometimes it's in the N, then it disappears and comes back again later on in the answer. Equal to 10 plus 2J ohms. Convert to does that fit in with civil? Reactance is positive, so we overall the inductive reactance is bigger. We've got an inductive circuit. We end up with a positive overall impedance angle. Current I get 2.35 amps, angle minus 11.3 degrees, and if we check that with civil, we'll find that in an inductive circuit we should have a current that lags the voltage. Yep. Okie dokie. Everyone got what they want from that? Okay, one for you guys to have a go at now. Five ohm, 10 ohm, 15 ohm, 60 volts, angle 0 degrees. IT, VR, VL, VC. So, calculate total impedance, total current, calculate the voltages VR, VL and VC, the 3 volt drops across each of the components, and prove KVL for the circuit, i.e. VR plus VL plus VC equals VS. Make a start on that.